The title of my talk is Process Causality and Non-Commutative Probability 1, because I will talk also on Friday. So this is the first part of my talk, from categorical structure to consciousness. Okay, so let's me explain the overview of my talks. The title becomes category. This is process and the causality and non-commutative probability, and the logical relationship is this direction is natural as a mathematician. But I think that all in this context, many of you are interested in quantum kind of thing after the talk of now. So I will begin with this part, non-commutative probability, and explain what is the relationship between categorical structure and non-commutative probability. This is today's talk. We will talk about the notion of category algebra and the state on category based on the notion of category. So let's start. First of all, I would explain what non-commutative probability is. In a sense, the non-commutative probability is a generalization of the usual probability theory, which can include quantum theory, mathematical aspects of the quantum theory. The basic ingredients of the non-commutative probability is the notion of non-commutative probability space. What is this? Over here, C is a complex number, field of complex number. But it can be generalized very much like called rig. Rig means that some kind of number system which is equipped with sum and product, addition and multiplication. Not necessarily need to have does not need to have minus. So you can generalize it. But for the study of quantum physics, it is conventional to start with this scalar as a complex number. So I will explain it in a while for a while. So the basic ingredients of non-commutative probability spaces, first one ingredient is star algebra. What is algebra? Algebra is a vector space equipped with multiplication. The vector, almost all of you are familiar with at least some kind of vector space. For example, the Rn, Cn, so the set of n tuples of numbers has addition as usual, component-wise addition, and scalar multiplication as a component-wise operation. So this is a vector space. But there is a very good vector space which equipped with multiplication. The example is the matrix algebras. Matrix algebras has addition. If you fix for the n by n matrix. And also the matrix has a multiplication. So this kind of thing is called algebra. Of course, there is many algebra like polynomial algebra, which is high school students also know about. And also in classical probability, algebra of random variable plays a central role because random variables is the most important notion, at least in application of probability theory and statistics. Intuitively, random variable is something, some quantity which depends on some randomness. And you can think of the random variable x and random variable y and addition of this. Then this also becomes a random variable. And also the important thing is we can define the multiplication of random variable. Because without this kind of notion, you cannot talk about the correlation or independence or something like that. So to do statistical theory, we need not just a random variable, but algebra of random variable, okay? And also, to include the quantum theory, we need a star operation, which is a generalized notion of Hermite conjugate, or more generally, the complex conjugate. This notion is important to talk about the positivity of something, because in for real numbers, the square real numbers should be equal or larger than 0. But in complex numbers, we need to have the conjugation, complex conjugation. Like for this, we define this. This kind of thing is also called the complex conjugation. So this conjugation, generalization of this conjugation is called star operation. Then star algebra is nothing but the algebra which is equipped with star operation. Star operation obeys this rule, like this, twice is nothing, and linearity or the anti-linearity is. But these are technicalities. So the star algebra is the generalization of algebra of random variables and also the matrix algebras and polynomial algebra. So it's something else. Then we want to talk about the generalized notion of statistics. So we need the notion of state, because random variables talked about this x and y, but the important thing is expectation value of random variables. If the probability measure is given, you can talk about if the probability measure has all the moments for the mathematicians. But if you talk about probability nature, we can talk about expectation value. And certain reasonable condition that this can be reversed direction, that if you are given the expectation for all the random variables, then you can talk about the probability distribution. So to talk about the statistical thing is nothing but to talk about the mapping from random variable, algebra of random variables into the number, expectation value. Then this E, the mapping, is called the state in general setting. What kind of general setting? That is, if this is the non-commutative, then there is no such a probability distribution in general. And in quantum theory, you cannot do everything within the classical probability theory, which is start from the probability distribution or blah, blah, blah. This is one of the reasons the Nobel Prize is given by the violation of Bell inequality. That is, the violation of Bell inequality means that not all quantum phenomena can be modeled within the classical probability space. Okay, so the state, the pair of the algebra, which is a generalization of algebra of random variable, and the state, which is a generalization of expectation functional, this pair gives you the generalization of classical probability space. And if you are familiar with the random matrix theory, then it is also an example of this kind of non-commutative probability space. My original idea is to apply this non-commutative probability theory, not only the quantum physics, but also the quantum cognition and the quantum qualia, now a little talked about. Okay, so we must, okay.
Good question, but I'm confused. Non-commutative is with respect to a pairwise operation, right?
No, this is an important point, but pointwise multiplication over the complex number becomes necessarily commutative. So there is another kind of multiplication which is not reduced to the pointwise operation.
Right. But so when we say non-commutative, for example, a multiplication can be non-commutative. Like
Can be non-commutative, like a matrix multiplication.
Right. So then, when you say a non-commutative space, is it because then is it the star operator? What makes it non-commutative? Is it the star operator?
This is the theme of my talk. So please wait. Okay. So I must do the remark that this non-commutative probability space, non-commutative probability theory is not the alternative of classical probability theory. No, it's generalization. So you can do all the classical probability theory within non-commutative probability theory. This is assured by famous, I think not famous for no mathematician, but Rees Markov Kaptanis theorem. This is a classical. This implies that the classical probability space is a representation of non-commutative probability space for the case that this algebra is commutative. Precisely speaking, the Qstr algebra, but we omit the technicalities. So the classical probability is a subsystem of non-commutative probability theory. So then what happens if this algebra is non-commutative? You cannot expect that this has a classical probability representation, but there is a universal representation of this abstract notion of non-commutative probability theory. That is called the Gelfand-Naimark-Saigo GNS construction. That is an NCPS, non-commutative probability space, can be represented on a Hilbert space. So starting from very abstract thing, we can reconstruct a Hilbert space. I think that for most of you, Hilbert space is very abstract, but for mathematicians, it's very concrete. So the point is, starting from the not necessarily commutative algebra and state, which seems to be the very light condition for the statistics. To do statistics, we need this kind of thing. Then you can reconstruct the Hilbert space. And this algebra can be represented as operator algebra of the Hilbert space. And the state can be represented as the vector in a Hilbert space. And also the expectation is, as if you are familiar with quantum theory, like the expectation is represented by the inner product or something, blah, blah, blah. Something plus quantum theoretical framework is reconstructed from this thing. So there is no surprise to model the cognitive or the Fourier structure in the framework of the Hilbert space. No mystery. If there is some kind of addition, multiplication, conjugation, and the state as an expectation function, this is very necessary thing. Okay. So back to the Alex's question. Why non-commutative? But anyway, do you have any questions? Okay, so the answer is in my opinion, the transition from the set to category gives you the commutative probability to the non-commutative probability. So let us remind of the notion of category. Thanks to the journal club so I don't have to repeat the definition of category, but check the intuition. The category is something like the system composed of something called objects and something called arrows. So this kind of thing. Of course, anything can be object, anything can be arrows, if it satisfies the axiom of category. But anyway, this axiom assures you that for any arrows you have the domain and codomain object, and if these pair is given, you can think of the composition of arrows, and the composition is associative. And for each object, there is a special arrow called identity arrow, which satisfies these kind of things. This is a category. So the relationship, conceptual relationship between set and category is as follows. Set is a special case of category which contains only identity morphism. Okay, so the category is more, how to say, organic. So the set is a very individual, the collection of individual independent things, and the category can include more connected, intrinsic connectivity for that system. And in this talk, category means a small category. Small category is all the objects and arrows is a set. Maybe infinite, maybe continuously infinite, but we mathematicians said it is small. So what is large? For example, the category of all the set and functions is called large because the collection set is not a set by Russell's paradox. So, but we avoid this kind of thing, the foundational thing, but just talk the small category. For example, if you are given the graph or manifold, then you can construct this kind of small category easily. For example, that the graph does not have the composition in general, but the path, if you talk about the path on the graph, then the path becomes arrows, and the connection of the concatenation path gives you composition. So if the graph or continuous case, the manifold, the point is object, and the path from point to point becomes the arrows, then these kind of things is also category. So in a sense, category is a very primitive notion of space-time. Okay, so then there is a special class of category called dagger category. Dagger category is a category equipped with a reverse direction operation, but not necessarily real inverse. Real inverse means that not necessarily to have this is equal to identity, this is equal to identity. If this condition satisfies, it is called a blue point, but we don't assume here. So this is a Venice Island, this is a San Salvador. The here is not identity because you experience the beauty of the Adriatic Sea or something. So it's not, life is not blue point. Life is like a dagger category. Okay, so in general, the category does not have this dagger operation. So for the mathematically oriented people, the typical example of dagger operation is Hermite conjugate. Hermite conjugate. Hermite conjugate is not inverse for the multiplication matrix in general. If so, it is called unitary. But in general, the multiplication is not inverse. The Hermite conjugate is not inverse. So this is a prototype of Hermite conjugate. And interestingly, every category can be embedded known to be embedded into some dagger category. Considering that as an example, I read you the definition of causality, but if you are given some causality notion, you can considering the indirect causal relation or something. So by this allowing indirect causation, we can construct a category. But this category is not dagger category in general because the cause-effects relation cannot be reversed in general. But in that case, even in that case, you can construct a zigzag construct. Zigzag construct is this kind of thing. Then this and this is not directly related by causation, but in a sense, indirectly related. This is very important in the quantum theory, like violation, Berry inequality or something. But if consider these relations as new morphism, then this gives you the dagger category, and this is called zigzag construction. And by this mathematical theory, the starting from, in general, irreversible feature can be embedded mathematically in some kind of reversible, not the groupoid, but the categorical structure. Okay.
So what you just drew, so there is then a morphism between these two things that do seem separate.
Yeah.
And that is a dagger.
Dagger, yes. So this zigzag contains this in series kind of arrow. So this is embedding. Okay.
So that zigzag, the essence of zigzag is that you don't have a direct causal relationship between A to B, but potentially if there is some kind of a common cause or something, then that's for the zigzag.
Yeah.
All right, in the example with the manifold, are the paths only the geodesics, or is it all possible paths?
All possible paths.
That's step one.
In that case, or if you talk about all possible paths, then you can think of dagger category. And in general, in Riemann manifold, the geodesics, so in that case also, okay. And more generally, the Finsler manifold or something is also can be considered as a category, and maybe this is, okay. So so this is, if this is causal category and this is extended dagger category, then we can talk about the talk below is concentrated on dagger category, but it is not the problem. Everything can be embedded in dagger category. So we focus on the case of dagger category buds. Okay. So far so good. The group category is this kind of thing. Then let's introduce the category algebra here. Category algebra, we can construct the algebra based on the category. So considering the function from the category, function from the set of arrows of the category. Then, for example, if f gives you some number a, g gives you 1 or this kind of function, alpha, another alpha dash, beta, gamma, you can think of many functions defined on the category. You can think of the linear vector space of these functions. And also, with some slight finiteness condition, you can define the product as a convolution. Product as this. This
from arrow to number.
Arrow to number. And by this. This is like here function alpha, here another function alpha prime. That you can define the alpha prime alpha as a multiplication as this. You can think of it, this is a function. So to define function, you need to define by the for arbitrary input, this arbitrary arrow to the output. So this is arbitrary arrow in category C. Then define as this. You can decompose this C as a here, this and this and this and this. Decompose all the possible decomposition. And here is alpha, the value, and the summing up. This is something like the Feynman's path integral, like so here to here, and the Markov. If you are familiar with Markov chain, this kind of operation is very familiar with. So, and actually the matrix multiplication itself can be understood as this. And also, if you are given the dagger structure, you can define the star operation by this. So dagger gives you star. This abstract definition of the convolution seems too difficult for audiences, but you can understand this very easily by introducing the notion of indeterminate, which is a generalization of Dirac delta. which is just this small c is arrow in the category. This iota c is the elements of category algebra, which is some functions on category. Function on category. What is this? Here C. This C can be identified with the function that the only C you give 1. As any other arrow is 0. This function is 1 to 1 and can be identified. So we denote iota C, and as a mathematical abuse of the notation, we say C equal iota C or something. Then, interestingly, this definition implies a very simple calculation rule. The calculation rule is that if C and C prime, in fact, this is iota C and iota C prime, but this C prime multiplication is given by the composition if the arrow is this pair, this kind of pair. But if the arrow is disconnected, the multiplication gives you 0. They're very simple. And so you can, or any high school students, I'm sorry, any high school students can do the category algebraic calculation as a class exam, because the rule is quite, so the F and G, this is arrow can be considered as a letter in the, okay. In general, the point is that in general, non-commutative, because, thank you for the question. Because let us take the very simple case. You can multiplicate this as this 1D is here. So you can multiplicate, because this pair is F ID is connected. So you can multiply by this kind. So sorry, F. This is F. But how about F1D? F1D becomes, this is F, but 1D is not connected. The codomain of 1D is D, and the domain of F is this. So this connected in this orientation. So this is 0. So F and 0 is not equal. So this is non-commutative. It's a very trivial example. Yes. But by using this exact construction, you can think of the new category as a category, and then you can think of in the zigzag category, you can do this kind, because it's a category. Oh, okay.
You say connected, there doesn't have to be an object in between. Can we just arrow on arrow?
Connected means that just the domain of G equals codomain of F.
But there is a dot, there is an arrow between, there's an object.
Object.
There's always one.
Yeah, because
it's connected, there's no object.
No object, yeah. Common object, no common object. So it is commutative. So the interesting is that if there is any arrow from the distinct object, then this category algebra becomes non-commutative. The only case the category algebra becomes commutative is the disjoint union of the commutative monoids. Commutative monoids is that the monoid is something like this kind of thing. And if this is more commutative, and then this is a case. The extreme case is the set case. Set is made of only identity morphism. Identity morphism is here to here, like object. So no non-trivial arrow between distinct objects. So in this case, this becomes commutative, and it is actually identical with the usual multiplication, pointwise multiplication. So,
can you repeat that? So it is commutative if the object between the arrows are monoids?
No, no. Only if commutative, the category has no arrows between distinct objects.
There's no errors between them. Then only then it's commutative.
Only then, yeah. So. Yeah. So only if I said only if the if and only if the disjoint union of commutative monoid and scalar is complete. Scalar is complete. Actually, okay. So this is very easy, but non-commutative multiplication. So the for almost all students, the first encounter with non-commutative products is matrix algebra. Actually, every element of category algebra can be represented as some kind of matrix, but infinite, in general, infinite matrix, as these indices correspond to the object here. This is a finite linear combination of arrows from C to C prime. Interestingly, this multiplication is nothing but the matrix multiplication of the infinite matrix, and by using some certain finite condition, that is, for each object there is only finite kind of non-zero arrow, and outgoing is all non-zero. This finite condition gives you the well-defined matrix, well-defined multiplication. So this is just a generalization of the matrix algebra. For example, considering this very simple category, which is these arrows is just a pair of oriented pair of this, then you give this category algebra is some 3x3 matrix algebra. So this is just a generalization. So far, so good. Okay.
So the example you just gave us is a star algebra defined for a dagger category. Is it unique? Are there others you could define, and this is just one example, or is this somehow a unique star algebra for this dagger category?
You say that every star algebra is generated by the dagger category?
So for a given dagger category, we can always do this. But could we do something else? Could we find a different star algebra?
Yeah, maybe. But it is quite a canonical construction. Yeah.
So this is just a convenient, always available.
Yeah, always available.
Does it have specific value, this construction, or are you just showing the existence?
By the definition of this, you can always be proved for the dagger category to star algebra. And this construction is a kind of functorial. There is a notion of arrows between categories, so-called retro functor, which is related to the functor. Then you can have the star homomorphism between by these constructions.
Am I correct in saying it a little bit like non-commutativity is actually more natural and normal? Commutativity is a special case.
Yes.
So we got it backwards.
Mm.
Why dagger category? In the dagger category case, this convolution is not commutative. So there is always inverted.
But yeah. Inverted, but inversion, reverse direction. But it is not related to the commutative or non-commutative. Because if you consider this kind of composition of arrow, the reverse is this. So reverse is, how to say, the other order. So it can be non-commutative.
I'm talking about the product transformation.
Mm-hmm.
I know if you think about like A alpha and alpha dash B,
Mm-hmm.
it can be the result, same result as the A dash B, alpha dash alpha C. Because we have
No, I will explain you, but no. The point is the Dagger category is a special case of category, and this definition of multiplication is valid for any category. And as I proved, if there is any arrow between the distinct object, it must be. Okay. 5 minutes. Okay. Then connect with the statistics. So then the state on category. What is the conceptual notion of state? As now, a little touch upon that. The state is something related to the background condition. In quantum physics, the algebras, so-called observable algebras in quantum physics, is some kind of mathematical tool which represents the intrinsic nature of the quantum system. And also the state is something that defined by the interface, as an interface of the system and the environment. So the same electron can have the many states if you consider the different environments. So this is state. And Dagger algebra from, we can construct star algebra from Dagger categories. Then this category algebra, on this category algebra, you can think of the state, of course, because this is star algebra. But in general, star algebra has not so much good concrete representation of the state. But for the category algebra, the state has very concrete representation. That is, in words, the positive semi-definite function on arrows. That means I would omit here what positive definite is, but you can think of the weight on arrows, which is such as some positivity condition. To define this positivity weighting and define the state is equivalent in a category case. So this is almost the last slide. My hypothesis and your possible question is, I think the category as a basis of consciousness, but of course this is argued. For example, even in IIT and of course in Fourier structure approach, you need all possible processes, all possible relationships, including the counterfactual things of certain kind is important. So if you consider some relationships, this is natural to consider as a category, like a similarity, association, and causality. Of course, this needs to allow some indirect things. But anyway, this becomes, in a sense, a category. Of course, it depends on what is causality. We discussed it Friday. And causality, why causality forms category or something is related. So, but you can argue that. And how to measure, this is experimental, but measure causality in the brain. It is very difficult and deep arms. Of course, then if the category is a basis, then you can talk about its qualitative and quantitative aspects of the experience by using category algebra. But there is a choice of scalar, real numbers or complex numbers, and 0, 1 or tropical. That means minimum and plus becomes this Rig structure. You can consider this thing. And the elements of the category algebra is quantity depending on arrows that processes relation. I think this is very closely related to some Fourier and sum and product, and product is non-commutative, and I strongly believe that this is related to the quantum Fourier structure. And the states on the category can be considered as states of consciousness, because the consciousness states are considered as a weight on arrow, as I mentioned. And the quantum, I omitted the detail, but analogically, the quantum observables can be considered as a generator of some movement. So such like the qualia maybe can be considered as generator of state change. So feel something is simultaneously changes the state of consciousness from these kinds. Of course, but this should be tested. And almost last thing is that inner product by GNS, Gelfand-Naimark-Seeger construction given by states, there you can think of the inner product by dividing the nilpotent or something. But anyway, this gives you essentially the inner product. So you can talk about metric space or something. So you can define mathematically the distance from this Korea and that Korea under the state. So I think this is related to the diversity indices like magnitude. And the representation theorem, GNS representation, says the Hilbert space technique may be useful in the study of Korea, like quantum Korea. And the last thing is that we need to discuss about the role of environment. I think that this role of environment should be represented as a state of these things. Thank you.
We start header spoke from 11 to 10. Okay. So please come back here and be taken first time.
Explained so well that even I can understand. Thank you so much. So I have a question. So a little bit the answer to my question is it is the pairwise operation of multiplication, right? So then in our cases, when the memory is non-commutative, it's unclear, is that multiplication? You know what I mean? It's more a metaphor than an actual operation, right?
Yeah.
Okay, there's some later, maybe if you have some time, I would really like to talk to you about this.
Yeah.
Because you said maybe it's not real numbers, and I have a lot of ideas.
Yeah,
maybe that would be great. Thank you. So,
And how does zigzag obstruction relate to quantum theory?
This on the quantum theory, physics.
Yeah.
Because in quantum theory, there is a observer called the algebra called observable algebra. That is X and P and many observables. Physical constants becomes algebra and star algebra. So this in quantum theory. Your question is how to
So the zigzag construction, like you said that you mentioned that it's related somehow.
Okay.
So I was trying to understand.
With a simple, the very simple example is harmonic oscillator. You know harmonic oscillator?
I have a very intermediate
Okay.
quantum.
But anyway, there is a quantum system which is analogous to the harmonic fluctuation, and in the quantum theory, there is algebra which is related to this is ground state, this is next level energy state or something, and this is creation and annihilation operator. But this creation operator and annihilation operator generates a star. So every quantum theory can be, if you have a given quantum model, you can identify what kind of star algebra it is. And every state, for example, you know the wave function or something like that. So the role of wave function is nothing but to calculate the expectation by
I don't understand now.